Last time we have solved examples of DFT. First example was calculating n-point DFT for a finite number of samples given in the example. So in that examples we have done a lot of calculations. It was so lengthy for calculations. We don't want that much lengthy calculations. So today we are going to somehow ease this process by matrix formulation in DFT. So we are going to derive a new formula that will reduce the number of computations. Let us see. We'll solve that example again and solve it with less number of computations. So we'll first write the formula for DFT and let us see how we can modify that formula. So x of k is equal to n varying from 0 to n minus 1 x of n. We'll write a formula in terms of Twiddle Factor n k, where k is varying from 0 to n minus 1. So we'll take a specific example of n is equal to 4 for simplicity. X of k is equal to, this range will change, 0 to 3 x of n, this factor, now 4, n is equal to 4 raised to nk, and as k is varying from 0 to 3. Okay, so for specifically value of n is equal to 4, we will calculate a 4-point DFT. Values of k will be 0, 1, 2 and 3. Okay, so we'll write all that values formula again. First we'll rewrite this function except this summation, writing all the terms. X of k is equal to x of 0, this 4 raised to 0, plus x of 1, this raised to, now n is equal to 1, so only k, plus x of 2, this 4 raised to 2k, and this 4 raised to 3k. Okay, now we'll write those 4 equations. For k is equal to 0, what will be the equation? X of 0 is equal to x of 0, this term will be 1, plus x of 1, this raised to, now k is equal to 0, so this is 0, so this all terms are going to be 1. So I'll not write that terms, I'll just write like this, 1 x of 2 and x of 3. Okay, now for k is equal to 1, x of 1 is equal to x of 0, again here 0 is there, so 1, plus x of 1, k is equal to 1, so this 4 raised to 1, plus x of 2, 4 raised to, now 2, x of 3 multiplied by, okay, here 4 is required, 3, now k is equal to 2, x of 2, x of 0 multiplied by 1 plus x of 1, now k is equal to 2, so here raised to 2, raised to 2 into 2, 4, 3 into 2, 6, k is equal to 3, the last value, x of 0 plus x of 1 raised to k raised to 3 raised to 2k, 2 into 3, 6, x of 3, 4, 8, 3 into 3, 9. So these 4 equations are with us now, and we'll try to write in the matrix form. So we are getting at the output this x of 0, x of 1, x of 2, x of 3 is equal to some matrix multiplied by, in every equation you can see x of 0, x of 1, x of 2, x of 3. Here also x of 0, 1, 2, 3. Here also. In these two equations also you can observe those values. So x of 0, x of 1, x of 2, x of 3. Okay. Now this is multiplied by. Now for getting x of 0, so you have to write this row multiplied by this column. So x of 0 is multiplied by the first element, that is 1, again 1, again 1, and again here 1. Next, for x of 1, this row, second row multiplied by this column. So x of 0 multiplied by 1 again. This is multiplied by 4 raised to 1. This is multiplied by raised to 2. Here last term, this row. Now x of 2, we can write 1, this term, and this term. 1 raised to 2, raised to 4, raised to 6. Now last, again here is 1 raised to 3, raised to 6 here, and raised to 9 here. Okay, so this is a matrix form we are getting out of this 4 equations. You can write similar kind of matrix for large number of points also. This is just an example where we are taking n is equal to 4, capital N is equal to 4. Okay. Now here we'll name this as x. Will they name this matrix? This is a n by n here 4. So we'll name it D4. Here small x, the input vector. So the formula becomes x is equal to dn for general case into x. So this is the formula for calculating DFT. Similarly, you can rewrite the formula for inverse DFT. X is calculated from 1 by n dn conjugate, because that minus sign, into capital X. So from this you can calculate the inverse. Okay, so these are the two formulas for DFT, and this is for IDFT. Okay, now you can observe here the values. You can calculate those values, write here that points and multiply it with the samples and get the DFT. Okay, so here again we are having challenge that those points like this 4, 6, 4, 9. So those calculations are increasing again. So we'll see one thing to calculate this. So major part we need to calculate in this example is that Twiddle factor. So Twiddle factor n Twiddle factor is equal to e raised to minus j 2 pi by n, and you know that this phasor is calculated from cos 2 pi by n minus j sine 2 pi by n. Okay, so what is the magnitude of this? Magnitude of this is magnitude of e raised to minus j 2 pi by n, and magnitude of this phasor is 1, because cos square plus sine square, and that is term is 1, square root of this is again 1. So this is 1. Angle of this is equal to angle of this term, e raised to j theta. So theta is this minus 2 pi by n, minus 2 pi by n. So this is the angle. Okay, so what if we are calculating for 4 points? Omega 4 1. Okay, omega 4 1. So omega 4 1 is e raised to minus j 2 pi by 4, okay, raised to 1. So this angle is 2 minus 2 pi by 4, means minus 90 degree position is there. I'll draw a circle here. Okay. So 4-point DFT. So this point is located here. Omega 4 1. This point at 0 angle is omega 4 0. This point is omega 4 2. This point is omega 4 3. Okay. Now again we can calculate and write this. Omega 4 4. This is equal to omega 4 5. This is equal to omega 4 6. This is equal to omega 4 7. Again it is equal to omega 4 8, like this. So its values we'll write here. It is unity amplitude circle, but its value is here at this point is 1, at this point minus j, this point minus 1, and this point is j. Okay, so these are pre-calculated values. You can check those values by putting this angle into this formula and taking cos and sine of that angle and calculate these values. Okay, now this is just for 4 points. If you want to calculate for 8 number of points, so 4 points we are dividing the whole circle into 4 points. Now if 8 point we want to calculate, you have to divide the circle into 8 number of points. Omega 8 1, this is 2, this is 3, 4, 5, 6, 7. Again this is omega 8 8. Okay, omega 8 9, omega 8 10, like this. You can go on writing like this. Okay, so I'm writing here the values. This value is 1, this value is minus j, this value is minus 1, this value is j. This value at this point 1 by root 2 minus j 1 by root 2, this value. This value is 1 by root 2 minus j 1 by root 2. This value is minus 1 by root 2 plus j 1 by root 2. This value is 1 by root 2 plus 1 by root 2. Okay, so these are again pre-calculated values. Just want to derive the properties of these values. Okay, we can term these axes as real of omega n, this axis as imaginary part of omega n. So you can see j here, real quantities over this axis. So you can observe that omega 8 0 is equal to omega 8 8. Here also we can observe the same thing, omega 4 0 is equal to omega 4 4. Okay, so you are traversing same number of point on the circle, you are going to get the same value. Omega 8 1 plus 8 is equal to omega 8 9. So you are getting the same value at this point. So this property is called as periodicity property of Twiddle factor. We can write this in general terms. We can write omega 8 k. Omega k 8k is equal to, sorry, here we'll write in general terms. So n omega n k plus minus n. So travel from omega 89 to omega 81 or from omega 81 to omega 89 plus minus n is written for this, you are going to get the same value. So this property is called as periodicity property. Okay. Now you can observe here, if you are traversing by half number of points, suppose this is 8 point circle and 4 points 1, 2, 3, 4. So the magnitude is reversed, 1 becomes minus 1. Again from this point if you travel 4 points 1, 2, 3, 4, so you are going to get plus 1. Okay. So in this circle also there are 4 points. If you are traversing by 2 points, you are going to get the negative amplitude. So from this point 1, 2, so this is minus j, this becomes plus j. From plus j if you are going to traverse again by 2 points 1 and 2, so you are going to get j like this. This is called as symmetry property. So it is by traveling by half number of points. Omega n k plus minus n by 2 is equal to omega n k with a reverse amplitude. So this is called as symmetry property of the Twiddle factor. So here you can write 2n, 3n like this. So you can write in general it is plus or minus r capital N. So integer multiple of n. Okay. Now again you can observe here, you can compare this point. Okay, this will compare this point. Omega 82 is equal to omega 4 1. Okay, omega 82 is equal to omega 4 1. So in general terms you can write it as omega n like 2k, it will become omega n by 2. So 8 by 4 2. So n by 2 number of points, this k is also half. So this becomes k. This property will require while the derivation of FFT algorithms. Okay, this is one very important property. And also there are number of properties we'll see. Now in general terms we can write omega n0 or omega nn. Omega n0 is equal to omega nn is always going to be 1 because this is on the same position. Similarly omega n by 4, quarter number of points, it is always going to be minus j, this point. Again half number of points, omega n by 2 is equal to minus 1 always, and this omega n 3n by 4 is equal to j. So this point is j, always it is j. Okay, so one more property we'll see, omega n inverse e raised to minus j, that will become plus j if we take inverse. So it is like taking conjugate now. Okay, so these are the properties of Twiddle factor. So we'll use these properties to write the matrix that we have derived before, D4 matrix. We'll write the values of D4 and do the calculation for the very first example we have solved in the last lecture. Okay. So I need this circle here. So I'm keeping this circle, rubbing all things. So D4, what was D4? 1 1 1 1. This again 1 1 1. Okay, this was only 4 raised to 1 raised to 2 raised to 3, 4 raised to 2 raised to 4, 6, 3, 6, 9. Okay. Now here we can change those values. Omega 4 2, it's okay, it is on the circle. It is also on the circle. Omega 4 4 is omega 4 0, so we can change it to 0. Omega 4 6, tell me which one value is that? Omega 4 5, omega 4 6, so this value is omega 4 2, so we can write 2 here instead of 6. Now omega 9, so omega 4 8 is this value, so omega 4 9 is this value, so we can write here omega 4 1 like this. Now we'll write this matrix. So this matrix will become 1 1 1 1. Okay, omega. Now this value 1, this value is minus j, this value is minus 1, this value is j. 1 minus 1 1 minus 1 1 j minus 1 minus j. Okay, so this is how you calculate D4. You can similarly calculate a D8 or any n by n matrix if you have all those points calculations, and you just need this matrix to calculate 4-point DFT. So we'll solve again that example. In the first example, x of n was given as, we'll solve the same example and see what time is required to calculate that. DFT of x of n is given as 0 1 2 and 3. Okay, and it is asked to find 4-point DFT of this x of n. So we'll write the formula. Now x of k, we'll write it symbolically. Okay, so we need this, x is equal to d4 into x. So we'll write d4 1 1 1 1 1 minus j minus 1 j 1 minus 1 1 minus 1 1 j minus 1 minus j multiplied by the example given 0 1 2 and 3. So here first sample x of 0, capital X of 0, this will be sum of all those points, that will be equal to 6. Now for x of 1 1 multiplied by 0 minus 1 minus j here minus 2 minus j minus 2 plus 3j. Now here minus 1 plus 2 minus 3 in the last row multiplied by this column, j minus 2 minus 3j. So this will be equal to final 6 minus 2 plus 2j, and this one becomes minus 2 minus 2 minus 2j. So you will check that the same answer is obtained using this, but in very few calculations you obtain this because this matrix is derived. Okay, so this matrix formulation reduces the time required to do all the computations. So this is a benefit, and it is very easy to solve with the matrix. Thank you.